to the right. Excuse me, I might have said left here. So we extend here, the exterior region is to the right. So we follow this around, and everywhere we have to make a choice, we choose to keep that exterior region on the outside, and we can follow and know that all of these edges are in the exterior region. So that's the 4 hash line and the 3 hash line are in the exterior region. So if we were to be doing a union here, this is incredibly simple, because all the way that's it, we're done. That's all it takes. So that we have the actually concave hole, the exact concave hole of this polygon, and that's all that we need to do. But if we continue on, there's some more things to see here. I wanted to talk about these intersections a little bit more, these nodes in the graph. If we look at them here, an intersection node will have the possibility of having regions attached to it. So in this particular case, this region that I've labeled A here is the infinite exterior region. We can make note that intersection 1, that A here is the infinite region, and D here on intersection 2 is the infinite region. Now, we have as many possible regions extending from this node as we have line segments coming into it. Now, there are no fewer than 3 line segments that come in, but there can be many that could come into the infinite number that could come into a node. Now, hopefully we don't run into too many cases like that. I don't imagine that we will. But anyway, we have these possible regions that extend from here. We found the exterior region, and so we'll exclude these 2 regions here from our searches here, from the rest of our searches. But let's start here at node 1, and we've eliminated A, so we're going to go into B. And so B is bounded by these 2 lines. If we take once again, we could order these by if we draw the horizontal axis here and measure the angle to each one of them, and then order them from smallest to largest. This possible region A is in between the lowest and the next, and so on. So if we come here at this possible region B, and we take the minimum angle line in that area, and follow it around. Let me zoom out here, and we follow it around. We always choose a direction that would keep that region, in this case, to the left. So we come here to C, and in order to keep the region to the left, we follow the 2 hash line, and we get back to where we were. And we're going to label this region 1. Okay? So then we're going to come on to this possible region C off of the first node in the graph. And then we follow its minimum 1, and we come around, and we call that region 2. And then we come out here to region D, and we follow it around, and we get region 3. Then we go on to the next node in the graph. In this case, every one of them is already found. So we don't get any additional information from that one. But we have basically the 3 regions of interest and the 4th infinite region, and this is all that we need to know to do all of our operations. Now, so I'm not sure what to call these interior angle possible region things. That's not a good name. We need something better. But if we want to do Boolean operations other than the intersection, say we want to do a difference of, let's make this more visible. So we have the 2 original triangles. We now want to take a look at these possible regions, these sectors. That's what they are. They're the sectors of each of the intersection points. We want to look at them in terms of the original shapes. So we'll call this triangle 1 and triangle 2. So triangle 2 had the node 1. It had the sectors C and D in it, and node 2, it had sectors A and B in it. So we'll make note that these 4 sectors originally belonged to this triangle. And we come out and look at this triangle, and we'll note that here in intersection 1, C and B were part of it, but not A and D. And And also we'll look over here at intersection point 2. B and C were part of triangle 2, but not part of triangle 1. Okay, so if we want to do an intersection, then we just look at all these sectors, all the sectors that belonged to both first triangle and second triangle, so that's only C and B, make up the shape that is the intersection of the two. It doesn't matter what crazy things this 2-hash thing does in between, because it has no intersections in between it. We know that whatever the shape of this region is, it is the intersection of these two. We could have other parts that were part of it, but this is a very simple case. Now let's say we do the difference. So let's say we have triangle 1 minus triangle 2. Well, so we take everything that was in triangle 2, or triangle 1, so C, D, A, and B here, and we subtract off everything that was in triangle 1. So we subtract all these off. So all that we're left is A and D. So this region here is what we're left with. And we could do the difference of this one minus this one as well. So A, B, C, D minus, B, C, B, C minus C and B, so it gives us this region. So that's all we need for Boolean operations. I think that's fairly straightforward. There may be some complexity to this that I'm not seeing right now. I hope not. But I think that's it. The best way to code this, I'm not sure at this point. I'll give my best stab at it. I imagine the things that we need to know after we have this graph is we need to know the horizontal angle of each one of the line segments that comes out of it, and we need to order those. We need to find the minimum point and then figure out this way to traverse things. We need I don't know, a graph traverse function or something like that that'll traverse and do what we want it to do, either stay on the right hand side or stay on the left hand side. So please let me know what you think on the CAM forum, or however you want to do this. If you want to do a video response, that'd be fine too. But anyway, that's it.